Okay, so today we're going to be looking at abstract pattern recognition. Now, one of the things with abstract patterns is that we can all intuitively figure out that there is a process going on. A leads to B, leads to C, leads to D, or maybe down here when we have a cyclical pattern, we know A leads to B, leads to C, leads to D, which leads to A again, and it repeats itself. These don't necessarily begin with numerical patterns, but they will lead into that, and we're going to see how we translate between the two in a later topic. So let's go ahead and get started. We have two different types of patterns, right? Up top, we see that we have linear patterns, which means A leads to B, leads to C, leads to D, and it doesn't necessarily repeat. When we get to cyclical patterns, the pattern loops back upon itself. We'll see the values repeatedly. So let's differentiate between the two. A linear pattern, the values do not repeat. Whereas cyclical, values repeat indefinitely. Perfect. So with a linear pattern, we're looking at the fact that with number 1, it looks like we have a husk of corn or an ear of corn, which is eaten by the mouse, which is eaten by the owl. The corn does not eat the owl. We're not using Lion King logic where we know the owl will eventually, go and become the grass, and the grass is, a version of the corn, and then the corn is eaten by the mouse again. We're looking at straight through. These values don't directly repeat each other. Same thing with number 3. We have another food chain pattern. The carrots are eaten by something, which is eaten by a fox, which is eaten by a lion. And so a lot of what we're working on today is just fine motor control. Let's make sure that we're working on drawing the best rabbit that we can. Because in this case, what a fox eats that also eats carrots is going to be a rabbit. So let's start out with whoop. Boop. There we go. So we have a nice little rabbit that is eaten by the fox, which eats the rabbit. It fits directly within this linear pattern. Now, the next one, number 5, isn't necessarily a linear pattern because we do know that time does repeat itself. And also, we're noticing that this abstract pattern, we might be able to add values because we notice right here we have 9 o'clock, 3 o'clock, 6 o'clock. We can add values into this, which means that we can manipulate this pattern numerically. But in the beginning, what we're focusing on is simply figuring out the middle part of this solution. Perfect. So we have a clock that's going on right here. Looks like from 9 to 3 to 6, it looks like 3 hours is passing each time, which means that in here it's going to be 12 o'clock. So both my hands are pointing due north. Sometimes with patterns like this, we could apply ages. I could say, okay, it looks like this is the life of an individual. It goes from baby to let's say child to young adult to old adult. So what comes before baby? Well, maybe we're at something where the baby is in the womb. So let's go ahead, add a little baby in here. That's our little baby. See, a baby is in the stomach here. So we could, again, theoretically, depending on the circumstances, we could add values for mass, we could add values for age. And we could say this is at age 0, maybe age 1, 8, let's say 20, and let's say 55 or older. So we can start taking these abstract patterns and practice applying the numerical principle to them. This one, a little harder so. Again, abstract patterns aren't necessarily something that we can immediately apply a numerical value, but we have grocery store cart, fridge, and plate. What comes before the two? Well, you might have somebody that is, let's say, I'm thinking of a chef. Let's draw a little apron on this chef. Who's grilling up the steak and looks like green beans. Perfect. Again, so with this, that'd be a little more difficult to apply a numerical pattern. But what I want you to do is I want you to take a minute and I want you to try and draw your own. We are going to move on, though, to the next set. So if we look at these are now cyclical patterns. These patterns will repeat themselves. So we're looking at some of these in a more holistic sense. We have eggs, which lead to caterpillar, which lead to something, and then butterfly and back again. So with this one, we notice this is a monarch butterfly, so I know that it's going to be a chrysalis. Let's draw something like that. Perfect. That's a beautiful monarch chrysalis. And again, this pattern, the values in this pattern repeat themselves. So I will see a caterpillar again once I loop around. I'll see a chrysalis again once I loop around. Same with monarch. I'm getting the same answers again and again and again. Where these, I did not. After I go to the grocery store, put it in the fridge, grill it, and eat it, that food does not magically become in the grill again. It doesn't show back up in my fridge. Now again, if we kind of zoom out of the situation and look at it from a larger perspective, yes, we know the food cycle does loop itself, but for this pattern, we're so close that this is a linear portion of it. Same thing with number 15. We have somebody at the gym, looks like at the beach, and then a laundry machine. So it looks like this might be a day. They go to the gym, they tan, they do laundry. Probably after that, I would say go to sleep. So how would we set that up? Well, let's draw some pillows, blanket, and then his head is sleeping on a pillow. There we go. Perfect. So again, these patterns, after he wakes up, he'll go back to the gym, tan, laundry, sleep, gym, tan, laundry. That pattern repeats itself. I'm getting these values again and again and again. So you could take a moment, draw your own cyclical abstract pattern. We're going to jump off into the next section. So this portion is going to be convergent and divergent patterns. So we're going to focus on other types of abstract ideas that deal with, again, these two terms, divergent and convergent. So let's take a look at what these two terms signify. Well, divergent, we have some Latin roots here. Di is going to be 2 from monoditritetra. Verge is going to be, we're going to use the term edge. So we have a 2-edge style pattern. Con is going to be together. And again, we have edge. So we have a 2-edge and a together edge. And so that pretty much makes sense. If I have a together edge, it looks like we're probably going to be approaching a single point, which is going to be our convergent. And then moving away from a single point to split or to fracture, we're going to go with our 2-edge style thing of divergent. You might ask, okay, cool. How does that necessarily apply to what we're doing here? So if we have a 2-edge style pattern versus a together edge, most of the time what we're referring to mathematically and the topics that we're going to see here are a together edge if we look at the number line and look at how these edges will work when dealing with values. We have 0 directly in the center. We have a negative infinity over here and a positive infinity over there. Our 2-edge style patterns are going to be patterns that go towards the 2 edges. So if I have a 2-edge here and an edge here, the edges of my number line are positive and negative infinity. So that pattern is going towards those two. They're getting bigger and bigger and bigger, probably oscillating between the two. A together edge is going directly towards this. So it might be oscillating on each side, it might be oscillating towards a value, but typically we're seeing convergent patterns converge on a value. We're going to go with 0 for this particular side, and the divergent patterns we're going to say are going towards the infinities. So let's take a look at a few of the examples. So if we look at number 17, it looks like we have a couple turtles. And the turtles are going from left, from 1 to 2 to 3 to 4. Now, this pattern right here is going to be more linear in nature, so it's not going to be the most true to our definitions, but these values are getting greater towards infinity because 1 to 2 to 3 to 4 is getting larger if we go with the number of turtles. And I'm going to ask that we write down something right here that denotates what we're measuring, the number of turtles. So from the left, the number of turtles is going towards infinity, which means that by definition, this isn't necessarily a convergent. We're going to call this a divergent, because we're going towards the infinity edge. Now, you could make an argument to say, well, it's converging on the value of infinity, and that would be a good statement. However, we're going to say that divergent patterns today are going to be going towards one of the infinities. From the right, we know that this is converging on 0. Now, these would be very different answers as opposed to the number of turtles. I said, how about let's go with the amount of free space in the ocean. And if I did that, the free space in the ocean with one turtle is really, really big. And the more turtles we get, the free space in the ocean gets very, very small, because now it's getting overcrowded. So I'd actually end up flipping these answers. So whatever the measurement that you're recording, go ahead and write that down and show where this pattern is heading off to. Number 19, it looks like we have what looks like a nebula, a moon, planet, a sun, a red giant, and a black hole. So what could we measure here? And this is where the abstract patterns start getting a little difficult. We could measure something, let's say the amount of gravity, and the gravity is getting bigger as we go. What we couldn't necessarily do for this pattern is go with size, because our nebula is going to be extremely big, our moon is small, and then it gets bigger, and the black hole gets smaller, but as the black holes keep going, the black holes keep getting bigger. So we can't go with size, but we can go with something like gravity. Okay. So from the left, the nebula's gravity versus the moon, the planet, the gravity is getting bigger. So from the left, gravity is going towards infinity. Again, you could make the argument this is converging on infinity, but we're going to call this a divergent pattern. And then from the right, as we go back down, the gravity is getting smaller. So we're going to say it's approaching 0. We know that the nebula, if you zoom way, 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 way out on the nebula, it actually has the full gravity of any of the things inside of it. But for the instance of this, we're going to say, again, it's approaching 0. Awesome. Now the last thing from the left to the right, let's take a look. We have an empty field, some farmland, some suburbs, and a city. So what are we measuring here? Well, we could say it's population density. What we couldn't say is the time of year, because that isn't something that I can necessarily measure from one to the other. It doesn't have any indication. So let's give it a value that looks like it's consistent across them. So population density. So the population density right here is very, very close to 0-ish. And as we move to farmers, farmers require a lot of land. Let's say that's a 1. Suburbs, maybe that's a 10. There's 10 people for each plot. And then the city, we might have something like 1,000. So again, from the left, it looks like we are approaching infinity, and we're going to call that divergent. It's going towards one of the edges. Now, divergent technically means it needs to go towards both edges, but again, we're just simply looking at where this goes. From the right, it looks like it's going to be approaching 0. At some point, we might hit 0 if all the humans are gone, but realistically, it's just going to get very, very sparse. And we're going to call this convergent. Awesome. And there we go.